Okay, it's time we talk about the quotient rule for derivatives. And here's the statement of the quotient rule. Suppose that f and g are both functions that are differentiable. Then we can take, suppose also that you're going to make another function, let's say big F, and that's just going to be combining f of x and g of x with division. So the quotient rule gives us a rule for finding the derivative of f big F. And it just says that that's equal to the derivative with respect to x of f divided by g, and that's just going to be g times f prime minus f times g prime over g squared. Let's take a look at an example of how one might use the quotient rule. Okay, so there's our first example. The function is a rational function. And so what we're going to do is, well, we're going to name the denominator f, and we're going to name the numerator f and the denominator g. And then we'll just plug in to the formula to find f big F prime of x. So we know that that's g times f prime minus f times g prime over g squared. So what would the setup of that look like? Well, let's do it a piece at a time. G is the first factor in the numerator, and that's just simply 3 minus 4x. And then times the derivative of f. So that is all times the derivative with respect of 2x of 2x minus 1. So that's g times f prime. And then minus f times g prime. And that's all over g squared. So that's going to be all over 3 minus 4x quantity squared. So that is what the setup would look like. On the next step, we're going to go ahead and find these derivatives. Afterwards, we're going to simplify. Okay, so then this is going to be equals to 3 minus 4x times 2. Right, what's the derivative of 2x minus 1? Well, it's 2. It's 2. And then minus 2x minus 1 times the derivative of 3 minus 4x, which is negative 4. And all of that is over 3 minus 4x quantity squared. So now we want to try to simplify that a little bit more. And one motivation for simplifying this a little more is later in chapter 3, we're going to have a need to have the derivative written in a simplified fashion, because we're going to need to work with it. Okay, so for now, let's just continue to simplify this. All right, so I'm just going to distribute 2 here and distribute negative 4 here. Okay, so that ought to give me 6 minus 8x. And then I'm going to subtract from that negative 8x plus 4. And that's all over 3 minus 4x quantity squared. Okay, so now I can get rid of the parentheses on the first quantity here. That's just using the associative property. And then I'm going to go ahead and get rid of the parentheses here by distributing the negative or the subtraction symbol. So that's 6 minus 8x plus 8x minus 4. And that's all over 3 minus 4x quantity squared. And you can probably see what's going to happen here when you add up 8x and negative 8x. That's going to zero out. And then 6 minus 4 is nothing but 2. So it looks like we're getting a fairly simplified version of the derivative function. And it looks like this. Let's go ahead and take a look at another example, and then we'll get into the proof of the quotient rule. All right, so we want to take the derivative. This time, the name of the function is r of x. And let's see if we can find something that is okay. How about this 2x squared minus 3x plus 4. And that's all over 1 minus 3x. Okay, so we want to find r prime of x. And so you can see that we're given a quotient here. So certainly you can name your numerator function f and your denominator function g. And then r prime of x will be given by the quotient rule. Okay, so it's g times f prime minus f times g prime over g squared. So let's go ahead and set that up. So it's going to be equal to g, or 1 minus 3x, times the derivative of the top of the numerator. So that's g times f prime. And then minus f times the derivative of g. And that's all over g squared. So it's going to be 1 minus 3x quantity squared in the denominator. So that's the setup. According to the formula, let's go ahead and take derivatives and then find the simplest version of this derivative function, r prime of x. Okay, so that's going to be equals to, let's see here, 1 minus 3x. What is the derivative of this quadratic? Well, it's going to be 4x minus 3. Minus 2x squared minus 3x plus 4, going along for the ride. And then what's the derivative of 1 minus 3x? I'm getting negative 3. And of course, that's all over 1 minus 3x quantity squared. Okay. Let's simplify this numerator as best we can and be done with this now. So I guess we're going to multiply here and multiply there. Okay, so I'll use FOIL technique on this. Okay, let's see, what did I do here? Looks good, plus a 9x. That looks like the mistake I made here is 3x times 4x is actually 12x squared. Okay, so we got that straightened out. Then this minus sign over here is right there. And we'll put some parentheses here because we're just going to distribute -3 over this quadratic. So that'll give us -6x squared plus 9x minus 12. And that's all over 1 minus 3x quantity squared. So it looks like we probably should double check things before we move on. It's certainly easy to make an algebra mistake. I know I've done it more than once, and I almost did it there. Hopefully this is correct. I've done some things to double check. Excuse me. So now I'm ready to remove the parentheses or distribute the negative over here. And also I'm going to combine these terms together. That's going to give me a 13x minus 3 minus 12x squared. And now remove the parentheses or distribute the negative. That's plus 6x squared minus 9x plus 12 all over that stuff in the denominator. It just keeps going along for the ride. It's g squared. And so we want to look to combine like terms. There's an x squared term here and an x squared term here. I can combine those together as -6x squared. There's an x term here and an x term there. So 13 minus 9 is 4. So plus 4x. And then 12 minus 3, that's going to give me 9 plus 9. All over 1 minus 3x squared. And so there's not a whole lot more we can do with this. Maybe we can factor the numerator. For now, I don't think we're going to need to do that. This is a lot more compact and simplified than any of our other steps. So let's go ahead and box this off and say that that's our prime of x. Okay, let's go ahead and take a look at the proof of the quotient rule, this statement right here. So it goes a little something like this. Let big F be made up of two different functions that are being divided, f and g. And suppose also that f and g are differentiable. Okay, so then if we use the definition of the derivative, the limit definition for big F, then we know that f prime of x is this limit. So now let's go ahead and expand that. All right, so keep in mind we've defined big F to be little f over g. And so what does that mean that f of x plus delta x is? Well, remember, you just have to replace the x in this definition with x plus delta x. So this first piece right here is going to be nothing more than f of x plus delta x divided by g of x plus delta x. So f of x plus delta x is just that. And then minus f of x, which is just little f over g. And all of that should be over delta x. So pretty complicated looking setup. And you may be wondering, well, where do we go from here? And I say that's a good question. So let me show you where we're going to go from here. So we're trying to prove this statement. We're trying to prove that this derivative will give us this formula, or will follow this formula for any two functions f and g that are differentiable. So there's our setup. And what we can do is, this is a trick I know we've used before, just to make things look a little simpler. I'm going to peel off the 1 over x. So I can write this as 1 over, I'm sorry, peel off the 1 over delta x. So I can write this as 1 over delta x times this big numerator right here. And then I want to add these two, or rather subtract these two fractions, and just make one fraction there. Okay, so I hope you can see what I did. I just peeled off the 1 over x, and I'm writing this as a product of 1 over delta x times that numerator. And when I come to subtracting these, when it comes to subtracting these two fractions, I've got to have a common denominator. And the common denominator is just going to be the product of these two denominators. And so therefore I need to multiply top and bottom of this first fraction by g of x. And the second fraction, top and bottom, needs to get multiplied by g of x plus delta x. Over itself. So on the next step, what's inside the purple brackets, I'm going to write as a single fraction, and the denominator is going to be g of x times g of x plus delta x. The 1 over x will be on the outside of that bracket, just to kind of get it out of the way for a second while I try to subtract these fractions. And so we're going to have a fraction with the numerator g of x times g of x plus delta x. So that's our denominator. Numerator will just be this minus that. So I can write it like this: g of x times f of x plus delta x. That's just this first numerator. And then minus f of x times g of x plus delta x. Okay, and so now it's time to play the same sort of clever trick that we used to prove the product rule, which is to add 0 to the problem, or in other words, add an expression and subtract that same expression. And we're going to do that in the numerator. Afterwards, we're going to factor and we're going to get the results. Okay, so take a look at what we're going to get here. Okay, and what we're going to do is we're going to take this first piece of the numerator, we're going to subtract from that g of x times f of x. And then we're going to add g of x times f of x. to the same numerator. And so when I take these two terms and I add them, I get 0. So we're adding and subtracting off the same term. So we're adding 0 to the problem. And then finally, this piece of the numerator needs to come down here. So minus that. And we're almost done here, folks, which is the good news. And that's all over g of x times g of x plus delta x. Okay, so I hope you can see what we've done. Again, we've just taken this expression, g times f, added it, and subtracted it here. So it's like we've added 0 to the problem. And so that's why these two statements are indeed equivalent. Okay, now what we want to do is I'm going to bracket off right here. So I'm going to group those two terms together. I'm also going to bracket off or group these two terms together. And of course, they're separated by the plus sign. And the reason I'm going to do that is in the first set of brackets, we can factor out a g of x. And in the second pair of brackets, we can factor out an f of x. So that's the next step, is to factor. Group and factor. And I think for simplicity's sakes, I'll put the delta x underneath the in the denominator. We'll just write one fraction now. So the g of x comes out of this first bracketed red expression. And so we'll have g of x being factored out. That's going to leave us with, of course, f of x plus delta x minus g of x. I'm sorry, f of x rather. And then this plus sign is here. And the second bracketed expression has the greatest common factor of f in it. So I'm going to factor that f out. And we'll be left with g of x minus g of x plus delta x. That's all over one denominator, delta x times g of x times g of x plus delta x. Okay, so we're getting a little bit closer to having the answer. And you must be wondering, well, where do we go from here? So the next step, there's going to be a lot going on. It gets fairly complicated, but let me explain it for you. I think one or two more steps and we're done with the proof. So go back to this step right here. Okay, we did the factoring and we had the 1 over delta x peeled off. Okay, and one thing that you can do, instead of writing the next step like this and putting delta x in the denominator, you can actually distribute, distribute 1 over x into the numerator. So I want to use this numerator and distribute delta x over that. Okay, so I'm going to do like so. Okay, so the one over delta x gets distributed into the first bracket, and then we're going to add that to the distribution of 1 over delta x into the second bracketed equation. So that's going to give us, but we're going to use this version, the factored version of that bracket, of that expression. So that ought to give us plus f of x. And all of that is going to be over g of x times g of x plus delta x, or g of x times that. Okay. So it's a pretty big limit statement there. Was going to just take it a step at a time. So now what I wanted to do is use the limit properties. Okay, so the first limit property I'm going to use is the quotient property of limits. And that just says the limit as x approaches a of f divided by g. Well, that's just equal to the quotient of the limits. The limit is x approaches a of f divided by the limit as x approaches a of g. So I can split that up into the quotient, excuse me, the quotient of two limits using your quotient rule for limits. So let's see what that looks like. So now this is equal to the limit as delta x approaches 0 divided by the limit as delta x approaches 0. So now we're just putting in the denominator and the numerator. So this will be g of x times g of x plus delta x. And the limit in the numerator, g of x. Okay, so so far so good. Now this piece is going to come down here. Only thing is, we're going to need to factor a -1 out of this so that it will be useful to use the definition of the derivative in the next step or two. So if I factor a negative out of the numerator, then I can change this plus sign to a minus sign. Okay, and then what's in this red brackets now? I can write it negative g of x plus delta x, or I can write it like this using the commutative property of addition and the definition of subtraction. Okay, so we're nearly done. What you might see here and there, it kind of looks like it's the difference quotient, and indeed it is. And so now the property of limits that we want to use, well, there's two of them. The limit, the difference property is one of them. The limit as x approaches a of f minus g, that's just equal to the limit as x approaches a of f minus the limit as x approaches a of g. So we're going to use that difference property in the numerator. But also in the numerator, I'm going to use the product property of limits. That's the one, yeah, that's the one that says the limit as x approaches a of f times g, the limit of a product, that's just equal to the product of the two limits. So in this numerator now, I'm going to use this property here, the difference property of limits, and the product property for limits. And so I can write the numerator now as the limit as delta x goes to 0 of g of x times the limit as delta x goes to 0 of this difference quotient here. And then finally minus the limit delta x approaches 0 of f of x times the limit delta x approaches 0 of this difference quotient up here. So these, again, these were the two properties that I used on that step. And all I did was rewrite the numerator. I don't want to forget to rewrite the denominator now. When it comes to the denominator, we can actually go ahead and evaluate this limit directly just by plugging in 0 for delta x. And that's going to give us g of x times g of x. So we can find that limit with direct substitution. It's just going to be g of x times g of x. All right, and then finally, this piece well, by definition of the derivative, that's f prime. And this piece, or this factor, by the definition of what a derivative is, that's the derivative of g, so that's g prime. Okay, and when you take the limit as delta x goes to 0 of g of x, well, you plug 0 in for delta x, there's no delta x there. That's okay, that limit will just be g of x. And then that's going to be times f of f prime of x, right? And then minus f of x times g prime of x. And that's all over g times g, or g squared, g of x, quantity squared. Okay? Or there's a shorthand way to write it, as I was doing before, it's g times f prime minus f times g prime over g squared. Okay, so that's the nasty proof of the quotient rule. Now let's go ahead and take a look at a few more examples. Okay, so here's a list of 5 more functions, and they all look like they're quotients. And we want to find the derivative of each one of these functions. So you might want to take a minute to write these down or pause the video here. Let's go ahead and take a look at the solution to the first one. So y is x squared minus 4 over x plus 2. And clearly that's a quotient. And so we could use the quotient rule. Only thing is that'd be a lot of work because the numerator does factor. That's a difference of 2 squares, that numerator. So it does factor down to x minus 2 times x plus 2. And that's all over x plus 2. And so you can certainly divide out a factor of x plus 2 and just rewrite y's definition as, well, just x minus 2, where x cannot equal negative 2, right? Because if x is negative 2, we get a division by 0. So x equals negative 2 was not in the domain of the original function, or the function as it was originally given. And so this is nothing more than a linear function, and it's going to be a line graph with a hole at x equals negative 2 in it. Okay, so to find the derivative, that's y prime. That's just going to be the derivative with respect to x of x minus 2. And of course, that's just going to be 1. So before you start to use your quotient rule, you want to ask yourself, is there any way I can rewrite this thing, this function definition, in a way that's simpler for me to take the derivative? And so this is one trick that you might need to deploy, where you factor and then you have a factor cancel. Let's take a look at the solution to the second problem. The function is y equals x squared minus 4x plus 3, and that's all over 2 times x minus 1. Okay, so that's the given function. We want to find the derivative. We can just go in blindly and use the quotient rule. However, that's going to be a lot of work. We should first investigate, can we rewrite this function definition in a more simplified form? One idea is to try to factor the numerator. And so if we did factor the numerator, how would that factor? I think it'd be like this: x equals x minus 1 and x minus 3. Would that work? So I believe that factorization does work. And then look what happens, right? We're going to divide out a factor of x minus 1. And so then the simplified form of the definition of the function is x minus 3 over 2, or you might get some use out of writing it like this: 1/2 times x minus 3. So when it comes time to taking the derivative, well, we just have to take the derivative of this linear function here. So y prime, or y prime of x, if you want to call it that, makes no difference. Y prime of x, dy dx. Okay, that's the derivative with respect to x of 1/2 times x minus 3. And I can pull that 1/2 out and use that constant multiple rule. Okay, so it's just 1/2 times the derivative of x minus 3. And the derivative of x minus 3 is 1. So this is just equal to 1/2 times 1, or just 1/2. So before you go in and you write that quotient rule out, well, maybe you need to find out if there's an easier way to rewrite the function first, and you may not have to use the quotient rule. Quotient rule is a pretty fairly nasty rule, and we try to only use it when we have to. Okay, so the next definition of the function y is this. We want to find the derivative of this function. It's another rational function, and it looks like this. And so if you look at it, hey, it's already factored for us. Is a factor going to cancel? No, it's not going to have a factor divide out. So if you try to set up the quotient rule right now, that you're actually gonna have the product rule nested within your quotient rule. If you try to set up the quotient rule with the function looking like this, you're gonna have the product rule nested inside of the quotient rule. So it's gonna be way too nasty. And one thing we can do to rewrite the function is just a multiply and combine like terms. So let's get that done now. So this is just equal to 2x squared minus 7x plus 2x minus 7 all over 2x plus 1. I'm going to combine the middle terms together. So I'm rewriting the function as 2x squared minus 5x minus 7 all over 2x plus 1. All right, so that's y. And it's going to be a lot easier, I think, folks, to use the quotient rule on this than it would be on this. Because again, if we use the quotient rule on this, you're going to have to use the product rule in the numerator. And nobody wants to do that type of a problem if you don't have to. So of course we're not done. We need to find y prime, or the derivative of y with respect to x. And that's just, of course, just going to be the derivative of all of this stuff here. And I think we'll just go ahead and use the quotient rule on that. And so I think what we're going to do is we're going to label that numerator our f and the denominator our g, so that we can write the quotient rule. Oops. So this is, yeah, this is just equal to g times f prime minus f times g prime. And that's all over g squared. Okay, so let's go ahead and set that up on this next step. Alrighty then. So g is of course just 2x plus 1, and then times the derivative of that numerator. What's the derivative of that numerator right there? So that should be 4x minus 5. F prime is 4x minus 5, right? And then we're going to subtract off f times g prime. So we're subtracting off the numerator. Times g prime, which would be the derivative of 2x plus 1. What's the derivative of that denominator? And I'm getting that it's just 2, just 2. And all of that should be, divided by g squared. So that's going to be divided by 2x plus 1 quantity squared. Okay, so that's what the setup looks like after we take the derivative. Now it's time to simplify that. So we'll multiply here. We'll multiply the 2 over here, and then we'll subtract, okay? All right, so multiplying here using FOIL, I'm going to get 8x squared minus 10x plus 4x minus 5. And then I'm going to subtract from that. Now I'm distributing 2 over this difference here, so that'll give me 4x squared minus 10x minus 14. Okay, so then all that's over 2x plus 1 quantity squared. Okay. So now I'm going to remove this parentheses and distribute the negative. Afterwards, we'll combine like terms, and hopefully we'll have a more simplified version of the definition of the derivative for this function. So that's giving us 8x squared minus 10x plus 4x minus 5. Whoops, I guess I can combine those together. I guess I'll do that on the next step. And then minus 4x squared plus 10x plus 14 all over 2x plus 1 quantity squared. All right, so we just combine some like terms now. 8x squared minus 4x squared, that's going to give us 4x squared. Right here, the 10x, the negative 10x and the 10x will zero out, and that'll leave us 4x, so plus 4x. And then 14 minus 5, that is, well, that's 9. And that's all over 2x plus 1 quantity squared. And I think that's about it. Do we need to factor the numerator? I don't think so, not right now. So we're going to call this the most simplified answer. So there, we did have to use the quotient rule, but first we want to multiply that numerator. I want to encourage you to try to get this same answer using this version of the function and seeing how difficult that is with product rule nested inside of quotient rule. Okay, so that's that one. And a couple more examples here. The fourth example, the function is this. X cubed minus 5x squared minus 6x divided by the square root of x. So that is a quotient. But I noticed the denominator is just one, there's just one thing or one term in the denominator. And so we can probably just simplify or rewrite this function to make our lives easier. And we might not even have to use the quotient rule on this one. So here's what I'm going to do. I'm going to rewrite the function definition. It's just x cubed minus 5x squared minus 6x. And I'm rewriting square root of x is x to the 1/2 power. Okay, so denominator is now x to the 1/2 power. Okay, and now I can divide each one of these terms by x to the 1/2 power. So this is equal to x cubed over x to the 1/2 minus 5x squared over x to the 1/2. And then minus 6x over x to the 1/2. So now what I want to do is use the property of exponents to divide each one of these terms by x to the 1/2 power. Okay, so the first this first term should be x to the 3 minus 1/2 power, and then minus 5x to the 2 minus 1/2 power. So I'm just using the quotient rule for the quotient rule of exponents. That's the one that says this, the quotient of two exponential expressions, both having the same base x. You can write that as a single exponential expression in which you just subtract the powers. Okay, so that's what I've written. I've rewritten the first two terms. The last term is minus 6x to the, well, this is a 1, so 1 minus 1/2 power. Okay, so I haven't taken the derivative, but you can see what's happening. I'm going to be able to simplify these terms and then use the power rule for derivatives on this function without having to use the quotient rule. All right, so that's how I'm going to approach this problem. So then 3 minus 1/2, that's 2.5 or 5/2. So this is x to the 5/2 power minus 5x to the, well, it's 1.5 or 3/2 power, and then minus 6x to the 1/2 power. Okay, so now I'm ready to find the derivative. Dy dx is just the derivative of all this stuff. Okay, so we know that's just going to be the derivative with respect to x of x to the 5/2 power minus 5 times the derivative with respect. So I'm using the derivative properties. Minus 5 times the derivative with respect to x of x to the 3/2 power minus 6 times the derivative with respect to x of x to the 1/2 power. So it turns out on this one, no, I'm not going to use the quotient rule. Hey, I'm going to rewrite it, the function, and then take the derivative using the constant multiple rule and the power rule for derivatives. So let's go ahead and do that. Also, I use the difference rule for derivatives. All right, so this derivative here, the 5/2 comes down in front. And then it's going to be x to the 5/2 minus 1. And then minus 5 times, well, the 3/2 comes out in front. Right? The power comes down in front. It's now a multiplier. And then this will be times x to the 3/2 minus 1 power. And then minus 6 times 1/2 x to the 1/2 minus 1 power. So that's just me writing out the power rule. Okay, 5/2 minus 1, that's going to be 3/2. So this is 5/2 times x to the 3/2 power. And then I can multiply, treat 5 like it's a fraction, 5/1. Multiply those two fractions, so I'm getting minus 15/2 times x. 3/2 minus 1, that's going to give me 1/2. And then over here, you can treat 6 like it's a fraction, multiply 6/1 times 1/2. That's going to give us minus 3 x raised to the, in this case, negative 1/2 power. And so that looks fairly cleaned up. I know that the book doesn't like it if we keep these rational exponents this way. They like for us to convert these to radicals and use the negative exponent here. So I guess we could do that. This is 5. We could write it like this, 5/2. Or we could put the x to the 3/2 in the numerator. That'd be the same as the square root of x cubed. And then minus 15/2 well, times the square root of x. And then minus 3 over the square root of x. So it's not very nasty. I mean, it's not very nice looking. In fact, it's fairly nasty. You can even factor an x out from underneath this square root here. And you could write the final answer is 5x times the square root of x over 2. It's pretty nasty looking stuff. Minus 15/2 times the square root of x minus 3 over the square root of x. So something like that, I would say. The book doesn't like for us to have negative exponents in our final answer for the derivative. It doesn't like for us to have fractional exponents either. It wants to see the radical equivalent of that. Okay, so that was a pretty complicated one. You could also use the quotient rule here, and you might want to try that with the quotient rule, just to see if it's any easier to do that problem that way. So let's take a look at the last example now of the quotient rule. And it's for this function right here. Y is equal to 3 minus 2 over x. And that's over x plus 4. So we do have a quotient there, and we got a fraction nested within a fraction in the statement of the definition of the function y. And one thing you can do here is to try to simplify this or rewrite it before you take the derivative. And how would you simplify it? You can't factor. What were the other tricks that we tried? Just factoring, combining like terms, multiplying. Can't do any of that. Okay, but one thing you can do is, well, you can go ahead and subtract these two and make that into a single fraction. And then afterwards, you can use the definition of division of fractions. So I guess I'll do it that way. So now I'm going to treat this 3 like it's a fraction, so 3 over 1. When I subtract these two fractions, I need to have a lowest common denominator, and that lowest common denominator is going to be x. So that means I can change this numerator. Well, first let me write the denominator. This numerator, if I multiply top and bottom of 3 over 1 by x, I've got 3 over x. And then minus 2 over x. Just going along for the ride. And you can actually subtract those two, right? This is the same as 3 minus 2 all over x plus 4. Okay, so that's nothing more than 1 over x divided by x plus 4. Okay, and one thing you could try to do is, well, you could rewrite the numerator using the negative exponent rule, and then you could write the function like that. Afterwards, you could use the quotient rule on that. That is one option, and that would totally be fine. That would be one thing to explore. However, I'm not going to do it that way because there's another way to try this, is to just use the definition of division of fractions, right? You remember that definition? It just said that if you're going to take a over b and divide that by c over d, right? Well, that's just equal to a over b times d over c. So I'm going to use that definition of how we divide fractions. And how am I doing that? Well, I'm viewing the numerator as a fraction 1 over x, so that's my a over b. And all of that is over x plus 4 over 1. So I've got a fraction divided by a fraction, right? It's 1 over x divided by x plus 4. And so by the definition of division of fractions, that's nothing more than 1 over x times 1 over x plus 4. Or you could write it like this, 1 over x times x plus 4. Well, okay. Where does it end? Well, you could write it like 1 over x squared plus 4x. And so, look, this is what I was getting at. Yeah, back here, we can do quotient rule with that negative exponent. That the simplification of that might be particularly nasty. So one other thing you can try is to use the definition of division of fractions. It's the fraction in the numerator divided by the fraction, or divided by the denominator there. And so that's equal to a multiplication by the reciprocal, right? All right, so I like this version of y. And of course, we're not done because we're being asked to find the derivative. So let's go ahead and do that now. So y is equal to 1 over x squared plus 4x. Y prime, the derivative, that's just going to be equal to g times f prime minus f times g prime over g squared, right? And that's equal to some f over g, right? The numerator's f, the denominator's g. So we've got a definition for y. It'll match the quotient rule when we find the derivative. So let's go ahead and write the right-hand side of this. That's going to be x squared plus 4x times the derivative of 1. What's the derivative of 1? And it's 0. It's 0. And then minus f, or minus 1, times the derivative of x squared plus 4x. What's that derivative? I'm getting 2x plus 4. And that should all be over g squared, so x squared plus 4x quantity squared. And now when we clean up this numerator, well, this is going to zero out right here, right? 0 times that is just 0. So the numerator will clean up into negative 2x minus 4 over x squared plus 4x quantity squared.